let's suppose that we have something like x squared minus x minus 6, and we want to divide that by, let's say, x plus 2. Well, I mean, division, it's just the same as this, right? X squared minus x minus 6 over x plus 2. It's the same thing, right? And x squared minus x minus 6, I mean, we would just, factor that. The x plus 2's would cancel, and the whole thing would turn out to be just x minus 3. So when I do this long division here, that's what I would expect. Okay, so let's do that. So now, when you do polynomial long division, you're basically going to do what you do with numbers, except some different stuff. Okay, so let's see what that looks like. So one of the things that you're going to do, and it's kind of like what you do with numbers, because if you were going to do numbers, you'd take the number on the outside, so the divisor, and then you'd look however many digits down on the dividend that you have to do first, right? Well, you kind of do the same thing here, except for it's the first term of the dividend and the first term of the divisor. So I would just go x squared over x. Now, I always write this out, because every time I do this, there's always a temptation for somebody to say that's equal to... Somebody always says 2. And then, because you're not really thinking about it if you don't write it out, right? So I write it out so that it's clearly x, okay? And then that helps me, too, to kind of keep track of things as I go. Now, if it was numbers, you'd put that up top, right? Okay, so now, what do you do now? Well, you take that thing and you multiply it by x plus 2. That's what you do if it was numbers. So we'd have x squared plus 2x. But now here's where we have to be really careful, because let's think about what we're doing. The next thing we would do is subtract. But if I'm going to subtract x squared plus 2x from x squared minus x. Now, if I do that, it's really easy for me to make an error and not put my parentheses. If I'm subtracting more than one term, I have to have parentheses there, or I don't subtract the whole thing. I only subtract part of it. I add the rest of it. So what does this really turn out to be then? It really turns out to be x squared minus x squared minus 2x. So the thing that you might remember from high school is that you would change the signs and add. And that way you don't ever make that mental error. Okay, good. So now I'm going to change the signs and add. Now the first term is going to go away. Well, it better, because that's why you put the x up there in the first place, right? So then if that doesn't happen, then you've messed up already and you need to go back and reevaluate your life. Okay, so then you've got minus 3x, and if you were doing numbers, you'd bring down the next number, right? So we do that. We bring down minus 6. X goes into minus 3x. I would write that out again. That's negative 3. So I'm going to write minus 3 up here. And then I'm going to multiply that out. I'm going to have minus 3x minus 6, change the signs and add, and I wind up with 0, which I expected. That's the remainder, right? And this is exactly what I expected. It's the whole reason I did this was so that I could see the same result. Okay, now, but what if we don't have what if it doesn't go in nicely? What if it isn't a remainder of 0? Okay, well, let's suppose that we have something, and this is going to be a really, really important skill. Okay, so what if I had something like x cubed plus x minus 4, and I want to divide that by, let's just say x plus 6. Oh, wait, well, one thing here, I'm missing an x squared term, and I'm going to need it. Stuff's not going to line up right if I don't have it. So what I'm going to have to do is I'm going to have to put an x squared term in there, and if I'm going to do that, it's going to have a coefficient of 0 on it. Okay, good. Now I can go through this process. So now I just do the same thing that I did before. I'm going to divide x cubed by x. That's going to be x squared. So I write that x squared up there. Now I multiply. So I have x cubed plus 6x squared. Change the signs and add. And the x cubes go away. Again, they better. And then when I add 0x squared and minus 6x squared, I have minus 6x squared. Bring down the plus x. Now I go minus 6x squared over x. That's minus 6x. That goes here. I'm going kind of quick now. Is that okay? Everybody doing okay? Multiply it out. Minus 6x squared minus 36x. Change the signs. Add. The 6x squares cancel. We have 37x. This thing's blowing up fast. Doesn't look to me like it's going to go in evenly. Bring down the minus 4. 37x over x is 37. So I'm going to put plus 37. Multiply it out. I have 37x. 180 and 42, is that 222? So plus 222. Change the signs. Add 218. Well, x doesn't go into 218, so that's my remainder. What do you do with that? What did you always do with your remainder? After you went past the third grade and quit putting R 218. What did you do after that?
You made it into a fraction.
Yeah, you made it into a fraction, right? It's plus 218 over x plus 6. And there you go. Oh, I don't know. I might have blown something somewhere. Probably did. Where did I make a mistake? Yes, it's minus 218. No, it's minus 226. Yes, very good. Thank you. Yeah, I read that as a plus. So that is minus 226. This then would be minus 226 over x plus 6. Can those 6's cancel? Just kidding. Okay, good. So, are we good with that now?
Yeah, that makes a lot more sense.
Okay. And then the really cool thing, though, the really cool thing is the synthetic division, all right? Should we do that real quick? Okay, so let's do the same thing. We're going to use that same problem there. So what we're going to do, though, is we're going to realize that if x plus 6 was a factor, if it was, it's not, but if it was, then minus 6 would be a 0, right? So what I do is I take what would be a 0 if it was a factor, which would be minus 6 in this case, and I put it in a little half a box. And then I put all the coefficients of the dividend polynomial written out to the right. So I'd have 1, 0, 1, and minus 4. Everybody seeing where I'm getting the numbers? Leave a space, draw a line. I'm going to write above and below that line. Okay, so I start by dropping the first one down under the line. Then I multiply. That's going to be minus 6. Minus 6 times 1 is minus 6. I write it below the next term. And then I add. 0 and minus 6 is minus 6. And then I multiply. Minus 6 times minus 6 is 37. These numbers are looking similar, looking familiar. It's 36. Add, I get 37. Multiply, we figured that out a second ago. That was 222, right? That's minus 222. Add minus 226. Okay, now what we see down here is that those numbers are the same as those coefficients on the long division. And that's not a coincidence. That's how that works. And the last number is the remainder. So this would be x squared minus 6x plus 37 because I'm dividing a cubic by a linear, right? And then minus 226 over x plus 6. So that was a lot quicker. And you can do that when you have a linear divisor like that.
Where did the negative 6 come from instead of positive 6?
Right here, or the one on the outside. This one here. So if x plus 6 was a factor, then negative 6 would be a root, right?
Oh, okay.
Because minus 6 plus 6 would be 0.
I see.
So whatever makes that thing 0. So in other words, the opposite or whatever you got there. If it was x minus 6, you put 6. Okay? Now, one more thing that is not a coincidence that is extremely cool about this process. If you were to put negative 6 into x cubed plus x minus 4 and evaluate it, you would get, oh, that's not what I meant to happen. You would get minus 226. That's cool, isn't it? Got to admit. Yep. So that remainder is the value of the polynomial evaluated at that divisor value. Okay? Any questions there? And that's why when it's a 0, it went evenly, because it's a root. It is a factor. X plus 6, like here. If I was to use negative 2 on that first one, I would get 0 at the bottom because it's a root. It makes the thing equal to 0 because it's a factor. All those things are exactly the same. It's all 3 considerations of the exact same concept. If we had this right here, 0, I don't actually remember doing this in college. I don't know. It was just something cool that that you guys are getting the privilege to do that I didn't. I was deprived of the opportunity. So, like for instance, this right here. So we're supposed to evaluate this thing in terms of an inverse hyperbolic function and a natural logarithm. And we're supposed to click this icon to find the natural log evaluation or equivalence of the inverse hyperbolic functions. Okay. And then when you do, you get this bunch of formulas here. Okay, so here's what you find out. You find out that things like, and I tell you what, I'm going to be streamlined about this process here. You find out that hyperbolic sine of x is the natural log of x plus the square root of x squared plus 1. And that is true for all x from minus infinity to infinity. So for all x. Okay, so if I'm looking at this thing and I'm going, okay, well, I think I might need maybe some more formulas. What's something that occurs to us about this thing right here? What would you use for u? 8x? Okay, so let's do that. So we would say, let u equal 8x. Okay, then u squared would be 64x squared. Dx would be, du rather. Du would be 8 dx. And so I want 5 dx, right? So probably I need to multiply both sides by 5/8. So I'd have 5/8 du equals 5/8 times 8 dx. And so 5/8 du is equal to 5 dx. So I think we have everything identified, don't we? So we would have integral, and we won't consider limits at the moment. So what do we have? We have 5/8 du over square root 1 plus u square. And what would be our integral from there? Do we have a formula for that? So we would have 5/8 integral du over square root 1 plus u squared.
So like inverse hyperbolic sine.
I think that's right. I think it's inverse hyperbolic sine. Look that up. Okay, so let's Google that. If you don't, I mean, because of the section that this is in, we are suspicious that it might be a hyperbolic function, right? So Google it. Just Google hyperbolic trig function. Integral formulas or something. And so, I mean, it brought up derivatives for me, but the derivative of 1 over the square root of x squared plus 1 is inverse hyperbolic sine. Okay? Everybody finding it okay?
What exactly did you search?
I just typed in, I don't remember, hyperbolic trig function integral formulas. Hyperbolic trig function integral formulas. I don't think I could say that like really fast. So what do we got? We got 5/8 hyperbolic inverse sine u plus c. But now I need to make a substitution back, and my u was 8x, so this is 5/8 inverse hyperbolic sine 8x. And now I'm going to put my limits in since I have substituted 0 to 1/8. Okay, so we have 5/8. Now this is going to be inverse hyperbolic sine of 1, right? Minus inverse hyperbolic sine of 0. Okay, so now we need to remember, well, okay, what is inverse hyperbolic sine? And that's just formula, right? With the e's. So let's see. So, but now I think though that, well, here, let's do this. Let's see how we're going to figure this out. So now remember what we have here are inverse hyperbolic sine, right? It's inverse hyperbolic sine. Now, hyperbolic sine is e to the x minus e to the minus x over 2, right? But remember, okay, but now we've got inverse here. So when I do the inverse hyperbolic sine, I would get an x value back, right? Not the value that is expressed here. So the question is then, under what circumstances would I get 0 for this thing? Well, only if the top is 0, right? So in other words, e to the x minus e to the minus x would have to be equal to 0. And this is basically e to the x minus 1 over e to the x equal to 0. And then I have a rational equation, so I would multiply both sides by e to the x. So I'd have e to the x times e to the x minus 1 equals 0. So I would have e to the, now when I multiply with like bases, I add exponents, so that'd be x plus x or 2x. Or you could think of it as a square, multiply exponents. Same thing either way. Now, remember, we're talking about a one-to-one function, right? There's only going to be one value for x here. Well, what's the only way that I can subtract 1 from something and get 0?
If that thing is 1.
And the only way that I can raise e to a power and get 1 is if that power is, yeah, it's got to be 0. So 2x has to be 0, which means that x has to be 0. Okay. Okay, so now, so what did we just find then? I just found out, what value of x would give me 0 for the hyperbolic sine value, and that is 0. So what does that mean that the inverse hyperbolic sine function would be?
0.
Yeah, it has to be 0, right? It's got to be 0. Okay, so that's good. So so what have we figured so far? We figured that we have 5/8 inverse hyperbolic sine of 1. That last thing is 0 there. Okay, well, what about inverse hyperbolic sine of 1? Now, this is the answer that you're going to have in the Pearson MyLabs on because you're going to put two answers in there. You're going to put the inverse hyperbolic sine form, and then you're going to put the log form, right? And that formula is here. It says that inverse hyperbolic sine of x is equal to the natural log of x plus the square root of x squared plus 1. Well, I think I already wrote that down, didn't I? Oh, I did. Okay. Well, it looks to me like all I'm going to do is put 1s in there, right? So my log form for this result then is just going to be where I put 1s in for x, right? So I'm going to have 5/8 times the natural log of 1 plus the square root of 1 squared plus 1. Well, that's just 5/8 times the natural log of 1 plus the square root of 2. And that's it. So, here we go. Let's suppose that we have the integral of cosine cube x dx. Now, if you were going to do a u substitution and you saw a cosine in a function, what would you look for? What else would you look for?
A sine.
A sine. You'd really need a sine, wouldn't you? But you ain't got no sine. All you've got is a cosine. Well, but here's something I know. I know that I could write this as cosine x times cosine square x dx. And I could get myself a sine, couldn't I? Because cosine square is 1 minus sine square. So I could write integral cosine x 1 minus sine square x dx. Okay, now I would have integral cosine x minus cosine x sine square x dx. And I could make myself two integrals out of that thing. So I'd have integral cosine x dx minus integral sine square x cosine x dx. Now I think we can integrate that thing. Well, the first one's just going to be sine x, right? So I just have sine x minus, and then I'm probably going to make a u substitution for the second one, right? I'm going to go, okay, I'm going to let u be sine x, then du is cosine x dx. So I have integral u square du. So we have sine x minus 1/3 u cubed plus c, but u cubed is going to be sine cubed x. And there we go. That was pretty nice, wasn't it? Now, this is a strategy. So here's a strategy. If you have an odd number of a sine or cosine, the odd number of them, then use a Pythagorean identity. So if you have an odd number of sine or cosine, use a Pythagorean identity. Okay. But, you say, what if I don't? What if I have something like integral 0 to pi sine square x dx? So here I have an even number. And when I have an even number of, and don't have an odd number, all of them are even, then I'm going to use a half angle formula. So if you have only an even number of trig functions, use half angle formula. Okay, so I just need to remember what's the half angle formula for sine square. Let's see, I think it's 1 minus cosine 2x over 2, isn't it?
Sounds right.
Yeah, and if you don't remember that, just Google it. That's a rare one that I do have memorized because I've done it so darn many times, okay? So let's see then. I'm going to have integral 0 to pi 1 minus cosine 2x over 2 dx. Okay, so let's see. This I can do integral 0 to pi 1/2 dx minus integral 0 to pi 1/2 cosine 2x dx. And now that I can integrate. So let's see. We'd have 1/2 x evaluated from 0 to pi minus, okay, now I have a 1/2. Now I got to think about the integral of the cosine of 2x. What's that going to be? Integral of cosine 2x.
1/2 sine.
Yeah, you're going to put the 2 on the bottom, right? So that when you do the derivative, it goes away, right? You get back to where you started. So times 1/2 sine 2x evaluated from 0 to pi. So we have 1/2 pi minus 0 minus 1/4 sine 2 pi minus sine 0. So what do we have here? We have 1/2 pi minus, now what's the sine of 2 pi? Okay, but what's the sine of 0? Yeah, so the whole thing is just 1/2 pi, right? Are we in the kind of in the same spot here? Do we make our way down this far? Is this what everybody gets here? So, to go back over what we did here, I've got, I started by taking sine to the 4th and saying, well, it's sine square square, right? And sine square is 1 minus cosine 2x over 2. So that's my first substitution. Okay, then I multiplied out 1 minus cosine 2x times 1 minus cosine 2x, okay? And over 2. And then the 2, of course, becomes a 4 on the bottom. And then when we multiply this out, we get, 1 minus 2 times cosine 2x plus cosine square 2x. Now, the nice thing is that those first two terms integrate nicely, but we're left with another cosine square, but this time it's cosine square 2x. So I'm going to have to double that, right? You double it for the half angle formula. How dumb is that? And you get cosine 4x then, but you got to remember that you still have the 1 plus, and then it's still over 2. Okay? And from there, then you're just separating terms, and then you're just doing a straight integration from there. Okay? Any questions about any of that? So, what are our strategies? Our strategies are, if you have only an even number of trig functions, then use the half angle formulas. If you have an odd number of sine or cosine, use a Pythagorean identity. Integral tangent square x cosine cube x dx. Well, I think what I'm first going to do is think about the tangent. That's cosine, or sine over cosine, right? So I think I'm going to see if there's anything I can do here. So that's sine square x over cosine square x, and then cosine cube x dx. Okay, great. So two of those cosines canceled with the two on the bottom. So what we have then is integral sine square x cosine x dx. Okay, great. So now if I just say, okay, I'm going to let u be sine x, then du is cosine x dx. And now I have integral u squared du, so 1/3 u cubed plus c, so 1/3 sine cube x plus c. And there we go. What if we have integral sine cube x cosine square x dx? Okay, that's different from the last one. The last one, when I did my simplification, I wound up with 1 cosine. And actually that happened the other time when I had an odd number too, right? I was left with 1 cosine. Well, this time I've got 2 cosines and 3 sines. Well, I think what I'm going to do is I'm going to leave 1 sine out. So I'll have sine times sine square and then cosine square x dx. And I'm just going to make a Pythagorean identity again, with this time with sine square making it 1 minus cosine square, right? Because the derivative of cosine is the opposite of the sine. So I'm left with a nice derivative of cosine in here. So what do we have then? We have integral sine x 1 minus cosine square x cosine square x dx. Okay, so let's see then. That gives us integral sine x. I'll just distribute that cosine square. So I'll have cosine square x minus cosine 4x dx. And I can make 2 integrals out of that. So I'd have integral cosine square x sine x dx minus integral cosine 4x sine x dx. And now I can just do some simple u substitutions, right? So I can say, all right, in the first one, I'm going to let u be cosine x. then du is minus sine x dx. So minus du is sine x dx. I can do the same thing on the other one, right? Okay, good. So I'll just turn this into then two u integrals. And here we go. We'll have integral u square minus du. So I'll put the negative out front and then du. Minus integral u to the fourth, and then again a minus du. So I'll deal with that. So we have minus integral u squared du plus integral u4 du. I think that's how we're going to end up. Everybody good so far? Okay, so we have minus 1/3 u cubed plus 1/5 u to the fifth plus c. So we have minus 1/3 cosine cube x plus 1/5 cosine to the fifth x plus c. Allison, what would you do?
My first thought was like integration by
I
parts.
think that might be the thing to do. That's the thing that we figured out the other day, right? If we've got functions that just don't seem to be related, seems that maybe an integration by parts might be a way to get started anyways and see if that does something for us. So let's see, we need a u and we need a dv. Well, I'm thinking that u is going to be x because du would just be dx. That'd be really simple. And I'm going to say, okay, well, I'm going to let my dv, now I got to think about this for a second. So I've got sine cube x, right? So if my dv is sine cube x dx, I'd have to integrate that, wouldn't I? Okay, so I think what I'd need to do is I'd have to say, okay, well, that's also sine x 1 minus cosine square x dx, right? Because it's a sine x times a sine square, and sine square is 1 minus cosine square. So my v rather, is going to have to be the integral of that. So v is going to be the integral of sine x dx minus integral cosine square x sine x dx. Okay, so what's that going to be? Well, so that's going to be then integral of sine x is minus cosine x, right? Integral of cosine square x sine x. Is that going to be minus 1/3 cosine cube x? And then I got a minus out front, so that'll turn it plus. How would I make sure I got that right? How would I make sure I did that right? Yeah, just find the derivative. Yeah, I think what I'd do is I'd say, okay, well, if y, well, we'll call it v. If v is minus cosine x plus 1/3 cosine cube x, then dv ought to be equal to sine cube x dx, right? Okay, well, derivative of minus cosine x is minus sine x, isn't it? Well, actually it'd be plus sine x, wouldn't it? Because I'd have a minus. So I'd have sine x plus, now, derivative of 1/3 cosine cube x. 3's coming down, multiplying by the 1/3, that's canceling. And then it's going to be cosine square x. Is that it? Is that no? Because that's a chain rule, isn't it? Outside function is cube, inside function is cosine. So what do I do now?
Times by negative sign.
Yeah, negative sine x. Good job. Have to multiply by the derivative of the inside function too. Okay, so this is, and all that would be dx, right? And then what do we have? So we'd have sine x minus sine x cosine square x dx. Huh. What can I do there? Factor out a sine? Yeah, we could do that. Okay, so we'd have sine x 1 minus cosine square x dx. And yeah, 1 minus cosine square x is sine square x, which would be sine cube x. Okay, good. I'm feeling pretty good about my work so far. Next piece of paper. Let's take some of this with us. Let's take that with us. Oh, well, let's take more than that. Okay, so let's see. I'm gonna erase some of this because I don't need it all. What I need is what U is, what V turned out to be, and what dV turned out to be. Okay. Wait, did I do all that right? Yeah. Okay, so now I'm going to use my integration by parts, aren't I? So let's see. One, I'm going to do those right there. So I'm going to have integral x sine x 1 minus cosine square x dx, which is sine cube, equals to this x times minus cosine x plus 1/3 cosine cube x minus integral that. That is going to be minus cosine x plus 1/3 cosine cube x dx. That got tiny over there, didn't it? Okay, so let's see. So we've got, I'm going to go ahead and multiply through by that x. So we'll have minus x cosine x plus 1/3 x cosine cube x minus, I think I'm going to make two integrals out of that. Is that what you guys want to do? The first one will be a plus integral cosine x dx. The second one will be a minus 1/3 integral cosine cube x dx. So let's see, we have minus x cosine x plus 1/3 x cosine cube x plus, that's just going to be a sine x, isn't it? Minus, okay, now I get to integrate cosine cube. I'm probably going to call that cosine times 1 minus sine square, aren't I? 1/3. And I can do that because this will be cosine x cosine square x dx. We have minus x cosine x plus 1/3 x cosine cube x plus sine x minus 1/3. Okay, now this is going to be integral cosine x 1 minus sine square x dx. I think we're okay so far. I'm going to move that over to the next page. Is everybody okay if I flip the page? Okay, so let's see. We've got minus x cosine x plus 1/3 x cosine cube x plus sine x minus, now I'm going to make two integrals out of this. I'll have 1/3 integral cosine x dx plus 1/3 integral sine square x cosine x dx. Everybody hanging in there with all the algebra? Okay, so we have minus x cosine x plus 1/3 x cosine cube x plus sine x minus 1/3, okay? So integral cosine x is sine x. So we have sine x. Now, integral of sine square x cosine x.
U is sine x.
Yeah, if u is sine x, then I get 1/3 u cubed, don't I? So I'd have 1/3 times 1/3 sine cube x plus c. So now all we got to do is combine our like terms. So minus cosine x plus 1/3 x cosine cube x. Now I've got sine x minus 1/3 sine x, so that's going to be 2/3 sine x, right? So plus 2/3 sine x plus 1/9 sine cube x plus c. Let's remember some stuff about our trig functions and triangles, okay? So here's a nice right triangle, and there's a nice angle theta. Now, so I'm gonna, there's one thing I'm gonna remember, and then the rest I'm gonna understand. Okay, there's two things I'm gonna remember, and then the rest I'm gonna understand. The two things I'm gonna remember, the first one is I'm only gonna work with functions, not the co-functions. So what does that mean? That means sine, tangent, secant. Not cosine, not cotangent, not cosecant. So only the trig functions, not the trig cofunctions. And then the other thing I'm going to remember is that every time I work with one of these, I'm going to have a specific form. And these forms are going to be either x equals a sine theta, x equals a tangent theta, or x equals a secant theta. So that's real consistent. It's x equals a something, and then that something is always just a trig function. Now, what does this mean, though? This means that sine theta would be x over a, right? Just dividing both sides by a. Now, looking at my triangle here, and we'll do this for all three of these. Looking at the triangle, if sine is x over a, then doesn't that mean that x is on this vertical and a is on the hypotenuse? And it means that the other side, according to an old dead Greek guy, would be square root of a square minus x square. If x is a tangent theta, then that means that tangent theta would be x over a. That means that the vertical would be x, the horizontal would be a, and the hypotenuse would be square root of x squared plus a squared. Hey, remember that 1 over the square root of x squared plus 1? Remember that? Yeah, remember that from Calc 1, right? So here we go. We're starting to see some of this stuff where it comes from. Okay, so secant theta would be x over a. And so let's see, secant. Now that's 1 over cosine, right? So that would be hypotenuse over adjacent. So that means then that the hypotenuse would be x, the adjacent would be a, and then the vertical would be the square root of x squared minus a squared. Now let's look at all these forms here. We've got the horizontal being square root of a squared minus x squared. So there's a negative in there, right? And the x comes second, the a comes first. Then we've got the hypotenuse being square root of x squared plus a squared. There's no negative in there, right? That's addition. And then we've got square root of x squared minus a squared on the vertical, and you notice the x comes first. So we really have every form we could possibly have, right? Because we've reversed the x's and the a's in the sine and the secant, but if you reverse the x's and the a's in the tangent, it's not different, right? So we really have every form we could possibly have. Okay, now how do we use this stuff? Well, here's what we're going to remember. We're going to remember those. There was really two things, wasn't it? Okay, well, maybe there's a third thing. But really not, because you will never, ever in your life forget the Pythagorean identities, will you? They are ingrained in your being. If you get Alzheimer's, you will still remember the Pythagorean identities. So what are they? Well, you don't have to remember them. All you got to do is remember the first one. All you got to do is remember that sine squared theta plus cosine squared theta equals 1. You really don't have to remember the others, because all you got to do is divide by sine squared and cosine squared to get the other two, right? So if I was to divide both sides by sine squared, I'd have 1 plus cotangent squared theta equals cosecant squared theta. If I divide both sides by cosine square, I have tangent squared theta plus 1 equals secant squared theta. So I don't really have to remember those either. But we are going to use them. not this one so much. Okay? So we're set up. We're set up here. Now, what are we going to do? Well, let's look at an example. Let's suppose that we have integral square root 9 minus x squared over x squared dx. So I'm looking at these forms. Remember we talked about these forms. We had square roots. We have either a difference where the x comes second or a difference where the x comes first. Now what do I got?
The x comes second.
Yeah, I got a difference where the x comes second. Okay, that was the first one. Okay, so now I always do this. I don't ever not do this because you need it later. That was bad. That's better. So I have a right triangle. I know I'm going to use the sine. I'm going to have sine theta equals x over a. So I'm going to have sine theta equals x over. Now at this point, I'm going to decide what a is. A is the thing that's squared that's inside the radical, right? And that's going to be 3. So I'm going to make a substitution here, and that is that the sine is going to be x over 3. Okay, so what does that mean? That means that x is going to be equal to 3 sine theta. And that means that dx is going to be equal to 3 cosine theta d theta. Now, I don't just have x's over there. I got x squares over there. Okay, well, I got a couple of things. I got square root of 9 minus x squared. Okay, so that's going to be the square root of 9 minus the square of 3 sine theta. So that's going to be the square root of 9 minus 9 sine squared theta. That is going to be the square root of 9 times 1 minus sine squared theta. That is going to be equal to what? 3 times what? 3 times what? 3 times cosine? Yeah, 3 times cosine of theta, because 1 minus sine squared theta is cosine squared, right? Square root of cosine squared is cosine. So this is just 3 cosine theta. Okay, great. So what do we have then? We have the integral of, okay, square root of 9 minus x squared is 3 cosine theta. So I have 3 cosine theta over x squared. Well, x is 3 sine theta, so that's 9 sine squared theta. And dx is 3 cosine theta d theta. How are we doing here so far? Say again? You okay, Jason? All right. All right, so what do we got here? We got integral. Okay, so this is 9 cosine squared theta over 9 sine squared theta d theta. Now what? We do have 9 cotangent squared, don't we? So we have integral. Oh, actually, no, we just have cotangent squared, right? The 9's cancel. So we have cotangent squared theta d theta. So I got to figure out now, how does that integrate? I'm gonna reduce all this here. Okay, so how do I integrate cotangent square. Oh, wait a second. I don't really know about cotangent square, but what do I know about? What's that? Well, I know about tangent square, but what else do I know? I know cosecant square, don't I? I know about that one. Right? Because you know about secant square, right? What's the integral of secant square? Yeah, tangent. What's the integral of cosecant square? Isn't it minus cotangent? I think it is.
What's that?
We might have to look that one up. But let's make a substitution and get ourselves there and see what we're working with. Okay. So, you know, I erased that other Pythagorean identity. Maybe I shouldn't have. So let's divide both sides of sine square plus cosine square by sine square. So what I have is 1 plus cotangent square theta equals cosecant square theta. Now, I've got cotangent square, so what I'm going to do is I'm going to subtract 1 from both sides, and I'm going to find that cotangent square is cosecant square minus 1, right? So this whole thing then becomes integral cosecant square theta minus 1 d theta. Okay, now look up, please, the integral, or just look up the derivatives of your trig functions, or whatever you want to do. However you want to do that. And what do you find about the relationship between cotangent and cosecant?
Derivative of cotangent is negative cosecant squared.
Okay, so that tells you then that the integral of cosecant square is negative cotangent. Yeah. So let's see then. We've got minus cotangent theta minus theta plus c, right? Well, I wasn't supposed to have thetas in my answer. What am I supposed to have in my answer? X's. Okay. Well, let's see. Cotangent theta. Well, I made myself a nice triangle, didn't I? And that's how come I did that. So that I can just look at it and tell what I've got. Okay, so here's what we have. I'm gonna bring this out here and make it bigger and draw on it. Okay, so here's what I know. I know that the sine is x over 3. Okay, so that means x is here and 3 is here. And that means that over here is the square root of 9 minus x squared. Okay, so I'm starting with cotangent. So what's the cotangent of theta going to be?
Root of 9 minus x squared over x.
Yeah, very good. It's adjacent over opposite, right? So square root 9 minus x squared over x. Now, theta. Okay, now that's a problem. Theta. I mean, that's not a trig function.
Is it just the inverse sine?
Yeah, very good. Inverse sine x over 3, right? I mean, that's how we defined the thing, that the sine of theta was going to be x over 3, right? That was our definition from the start. So theta is the inverse sine of x over 3. Plus c. I think we did it. Oh, darn. Here's something cool. I can make it a different color. Ooh, there we go. There's our answer. All right, any questions about any of that? All right, so let's suppose that we have integral 1 over x squared over square root x squared plus 4 dx. You guys take a second and get started on that, all right?
What's that last one?
X squared plus 4. 1 over x squared times square root of x squared plus 4 dx. I was talking to my dad the other day, and he's watching these, by the way, because YouTube figures out who your people are. Hi, Matt. Hopefully you guys chose tangent. Is this where we get to so far? Did we get, hopefully at this point, somewhere along the line. Okay, so I think we get some 2's canceling and a secant canceling, don't we? So we get integral secant theta over 4 tangent squared theta d theta. That looks kind of like a pain. Anybody got any ideas? When all else fails, what do you do? With trig functions. Yeah, I mean, but when I'm looking at something like that, I'm going, I know about secant, square, and tangent, but I don't really know a whole lot about tangent, square, and secant. But what do you always do when you just like, well, I don't know what to do. Well, I guess I'll just do this. With trig stuff.
You just figure out it was like secant, over cosine.
Yeah, just like convert it all to sine and cosine, right? I mean, that's the easiest thing to do. So let's do that. So let's go 1 over cosine theta, and then 4 sine square theta over cosine square theta d theta. Okay, so where does that take us? That takes us to 1 over cosine theta, and then invert and multiply. So we'll have cosine square theta over 4 sine square theta. Is that what you guys got? And then that leaves me with, I'll put the 1/4 on the outside, and I'll have a cosine on top and a sine square on the bottom, right? I think we can work with that. So now we'll just do a regular old U substitution, won't we? Okay, so I'm going to say let U be sine theta, then du will be cosine theta d theta. I got to remember that now I've got two subs going along, right? I went from x to theta and now from theta to u. So I'm going to have to remember to substitute all that back as I go. So what do we have here? We have 1/4 integral u to the minus 2 du, right? And that's going to be 1/4 -1 u to the -1 plus c. So we have -1 over 4u, I think. Now u, sine theta. So going back now, we have -1/4 1 over sine theta plus c. Okay, that's -1/4. That's cosecant theta plus c. Okay, cosecant. Cosecant is a upside down sine, right? So that's going to be hypotenuse over opposite. So we have -1/4 hypotenuse square root of x squared plus 4 over opposite x plus c. So I guess we could write that as minus square root x squared plus 4 over 4x plus c. I think we could. Are you guys using tangent? I wouldn't. I'd just do a U substitution on that one. So the whole idea is, and I was so thankful that Jason said that, don't make it too hard. Because this is also going to come up. You're going to look at it, you're going to get so used to thinking about these trig subs that you're going to miss out, miss when it's actually not. I think we have a bit of a situation here, don't we? We don't have a nice square minus just the x square. We have something else. So I think maybe what we need to do is think about making a substitution maybe from the start. Like maybe what we should do is we should do something like, well, let's let u be 3x or something like that. And then u square would be 9x squared. Then du would be 3dx and 1/3, excuse me, du would be dx. Okay, so let's see. If that's the case, then, well, let's write it out. I'm going to ignore the limits of integration for right now. So I'd have 4 minus u square. Square root of 4 minus u square. And then I'd have 1/3 du. So really this thing becomes 1/3 integral square root 4 minus u square du. Okay. So now I'm working with a u now. I'm just going to have to remember that I'll have to substitute it all back at the end to get my limits of integration in there if I don't carry them along, which I don't think I'm going to do. Okay, so let's see. 4 minus u squared. So let's go back over here and look at our different cases. So if I have a minus and I have the x last, or the variable last, then that means I'm probably going to use the sine function. So let's do that. 4 minus 2 sine theta squared. This is going to work out much nicer. So we have square root of 4 minus 4 sine squared theta. So we have square root of 4 times 1 minus sine squared theta, or 2 cosine theta, right? Okay, now, then we need to think about du. So if u is 2 sine theta, then du is going to be 2 cosine theta d theta. So what are we left with here? We got a 1/3. We got 2 cosine theta and a 2 cosine theta d theta, don't we? So, looks like we got a 4/3 integral cosine square theta d theta. Okay, well, let's work with that. We're going to have cosine square theta. What am I going to do? Got an even number of cosines, right? So I think half angle, isn't it? So I'm going to go, all right, so I've got 4/3 integral 1 plus cosine 2 theta over 2 d theta. So we have, we'll make this into 2. Well, let's do it here this way. Integral 1/2 plus cosine 2 theta over 2 d theta. So we'll make two integrals out of this. So we'll have 2/3 integral d theta plus 2/3 integral cosine 2 theta d theta. So we're going to have we're going to have 2/3 theta plus, okay, now the integral of cosine 2 theta. 1/2 sine 2 theta. So we have 1/3 sine 2 theta. Now, plus c. Now, we're out of time, aren't we? So, yeah, the other class needs to come here. You want me to finish this up real quick? Probably should. Okay. So, theta then is going to be, so our substitution was sine theta equal to u over 2. So that means that theta is the inverse sine of u over 2. But we made a substitution in the first place, and that was that u was going to be 3x, right? So this will be the inverse sine of 3x over 2. And then sine 2 theta is 2 sine theta cosine theta, right? Your double angle identity. And so this is going to be 2, okay, now sine theta, u over 2 times the square root of 4 minus u squared over 2. So far, we would have 2/3 inverse sine 3x over 2 plus 1/3 times 2 times u is 3x over 2 times the square root of 4 minus 9x squared over 2 plus c. And now we want to evaluate this from 0 to 2/3. So simplifying then, we would have 2/3 inverse sine 3x over 2 plus 1/6 1/2 x square root 4 minus 9x squared, this whole thing evaluated from 0 to 2/3. So this will be equal to 2/3 inverse sine 3/2 times 2/3 minus inverse sine 3 times 0 over 2 plus 1/2 2/3 times the square root of 4 minus 9 times 2/3 squared minus 1/2 times 0 times the square root of 4 minus 9 times 0 squared. And all of this then is equal to 2/3 times the inverse sine of 1 minus the inverse sine of 0 plus 1/3 times the square root of 4 minus 4, which will be 0, minus 0. So we have 2/3. The inverse sine of 1 is pi over 2, minus the inverse sine of 0 is 0. So this whole thing would be equal to pi over 3.